Mechanics, dynamics. The problem about the spool and thread. We have a spool with the outside radius r and the inside radius small r, and we have thread which is wrapped around this small circle. We put all this construction on the table with the coefficient of friction mu. This spool has mass m, and it has a moment of inertia I equal 1/2 mr square, and we apply tension T to this thread and the angle theta to horizontal. We need to investigate this problem with several cases, how it will behave for different tensions, for different angles, whatever. So first of all, we can make a quality search. If we take a look on this picture, we can see that in the point of connection we have normal force and we have force of friction which are going through this point. And the thing is, how is this tension T applied to this spool. If this line going to the left from this point of contact, it creates a clockwise moment, and this spool will rotate clockwise. If this angle big enough and this line going on the right from this point of contact, this spool will rotate counterclockwise. So that's quality. And the other thing is that we know if this tension small enough, there will be no sliding, and if it's big enough, there will be sliding. So we need to investigate this two cases. Suppose that T is small. We can write equation for linear motion that will be ma equal T multiplied by cosine theta minus force of friction, and we have rotation I alpha equal, now force of friction going positive clockwise direction, so that will be F multiplied by big R minus tension which is creating counterclockwise moment, so that will be TR. We have two equations, and we have A alpha and force of friction, but because we don't have sliding, it means that we have kinematic relation, that alpha equal A over R. This is how linear acceleration connected to angular acceleration. And because I equal 1/2 mr square, we can substantiate these two parameters to this equation. So we have 1/2 mRA equal FR minus T small r. And now we can eliminate force of friction and find what is acceleration. From this equation we have force of friction equal T cosine theta minus MA, and we can put it in here. So we have 1/2 MRA equal force of friction, that's a TR cosine theta minus MRA minus TR. And now we can move this part to the left, and we have acceleration equal T over M R cosine theta minus small r divided by 3 over 2r, which is equal to 2 over 3 T over M. And here we have cosine theta minus small r over big R. If we look at this formula, it's obvious that if we have small angles, this cosine very close to 1, which is greater than r over r, and the acceleration will be in to the left, which is correct, because due to geometry, cosine theta greater than small r over big R means that this line going crossing this base to the left from this point. And if angle is big enough, so acceleration going to the left. And the same thing with the angular acceleration. To find it, we just need to divide this by big R. The last thing is we need to investigate how big could be this T, because if a T is very big, force of friction cannot exceed mu multiplied by normal force. And let's see what it is. We have force of friction, we have this equation, so we have force of friction equal T cosine theta minus MA, which is 1/3 cosine T multiplied by cosine theta plus 2r over r. This is force of friction. And we need to calculate what is normal force. Normal force equal mg minus t sine theta. And we know that the force of friction, it cannot exceed mu normal force. 1/3 T cosine theta plus 2r over r. It must be less than mu mg minus mu t sine theta. And finally we have this expression for tension. We have tension less than mu mg over 1/3 cosine theta plus mu sine theta plus 2r 2/3 r over big R. So this is our relation. If t less than this expression, we don't have sliding. If it's more, we have sliding, and we need to investigate this case. Now suppose that tension T is big enough that we have sliding. Again, we have formulas. MA equal T cosine theta minus force of friction, and we have I alpha equal F big R minus T small r. Same equation, but the difference is now that force of friction F, that's equal mu multiplied by normal force, and normal force is mg minus which is mu multiplied by mg minus T sine theta, and we can insert it to these two formulas. So we have MA equal T cosine theta plus mu T sine theta minus mu mg. This is for equation for linear motion, and for rotational motion we have 1/2 m r square alpha, that's equal mu mg r minus mu t r mu t r no we have 1/2 m r square alpha equal mu mg r minus mu t r sine theta minus tr. And from this formula we can calculate what is alpha. So these two equations, they are separate because alpha is not connected. Alpha is not connected now kinematically to acceleration. And we have acceleration equal t over m cosine theta plus mu sine theta minus mu g. So that's the answer for acceleration, and for angular acceleration we have that's equal to times mu g over r minus 2 times t over m mu r sine theta plus small r. So this is the answer for angular acceleration. I guess that's it.